This film is a condensed report presenting the pictorial highlights of the Atlas missile program for the last 3 months of 1957. The most important advances in production concerned modifications in missile design and the transition in final assembly to B-series production. A milestone event during the quarter was the successful flight test of Missile 12A. On the first 2 flights of the Atlas, problems were encountered which made it necessary to destroy the missiles early in flight. Even though all flight objectives had not been attained, flight intelligence obtained during the tests provided an excellent basis for a detailed study of the problems. This study was undertaken at the contractor's San Diego plant. The magnetic tape is the history of an Atlas flight. On it are 200 separate signals transmitted from the missile during the test flight. This compact flight record was broken down into its individual signals as the first step in evaluation of the flight. These signals were then transposed onto visual media. From graphs such as this, engineers created a permanent record of flight performance. In test evaluation, analog trace lines are given numerical values, automatically recorded, and punched onto IBM cards. The IBM cards are mechanically monitored and provide the signals which automatically plot the test values as a function of time. After evaluation of the data, the cause of malfunction appeared to be excessive heat from the rocket exhaust and a 17 cycle per second vibration in the missile airframe. Working from this conclusion, the engineers proposed certain design changes. A series of tests was scheduled to prove out the proposed changes. At the autopilot test stand, engineers set about to solve the problem of an oversensitive flight control system. The gyro canister was installed in its flight position, and booster chambers gimbaled to duplicate conditions encountered in flight. From these tests, engineers were able to recommend specific changes in the electronic system, designed to eliminate the 17 cycle per second vibration. This is a breadboard, or working model, of a new autopilot filter. It was integrated into the control circuit for evaluation. This simple lag filter was designed to override the control system, and a production model designed for installation in existing autopilot canisters. The problem of overheating was first attacked by roughing out proposed airframe changes on a 1/30th scale functional model of the missile. In this preliminary study, the models were altered to duplicate proposed changes in the missile thrust structure. Tests included a study of an angled turbine exhaust duct. A small wind tunnel was used to simulate the flight airstream. Comparisons were made of heat patterns resulting from changes in the air eddy currents. Small tests such as this contributed greatly to the eventual solution of the flight problem. To solve the vibration problem, engineers conducted studies both in the laboratory and in the field. This is Sycamore Canyon Stand 1. In tests here, flight vibration frequencies were programmed to the missile control system. This is a view from one of the cameras inside the engine compartment as the missile is vibrating at 17 cycles per second. Those systems which showed a resonance to the flight frequencies were pinpointed. Corrective action was based on data from vibration studies such as this. This is static test stand 1A. The detailed support tests were integrated into large-scale tests at Edwards Rocket Base. In this series of static firings, flight vibration frequencies were programmed to the missile control system. An effort was made to induce the flight malfunction on test missile 2A. These flight backup tests completed the program with missile 2A, bringing the total run time to 1,050 seconds, of which 776 were accomplished in the last quarter of 1957. The major fixes are summarized in this drawing. They were stronger attachment of pods, a filter for the autopilot, addition of high-temperature plumbing and wiring in the engine compartment, a reduction in the length of engine nacelles, shorter fairings and redesigned heat shield for the thrust section, and an angled turbine exhaust duct. At the contractor's San Diego plant, the modifications were integrated into the production schedule. This view shows the installation of the fiberglass heat shield on Missile 11A, 6th flight missile. Before these changes are made to the birds, they are first proven on the full-scale proofing mock-up. Here, progress is one step ahead of production. This is the B-series model. The unit is used as a development tool and reflects latest design improvements. Engineers use the mock-up to solve manufacturing problems before they become production problems. The model in the background was used in developing the Series A Atlas and is now being converted to a mock-up for development of Series C. This activity will coincide with the beginning of Series C airframe fabrication. In final assembly, the last 3 months of 1957 saw the phasing in of B-series production. Simply stated, B missiles differ mainly in the addition of the third barrel to the power package. This is the sustainer engine. Attachment is directly to the aft cone of the propellant tank. The sustainer provides an additional thrust of 55,000 pounds, sustained over a longer period of time, 3 minutes beyond the time of booster shutoff. The added power of this engine will increase the Atlas range to the required 5,000 miles. The booster section for the B-series is the missile's first stage. This entire section is staged or discarded from the bird after the first 2 minutes of flight. Staging is accomplished by means of explosive charges. The rails guide the unit until it is clear. This was Missile 1B early in the quarter. It is a static test atlas which will begin its test cycle at Sycamore Canyon during the first quarter of 1958. It was one of 7 Series B missiles in final assembly at the end of 1957. Missiles now in production will have the improved booster engines which will provide a booster thrust of 300,000 pounds. On December 21st, a double missile convoy left the San Diego plant en route to Cape Canaveral, Florida. The 2 missiles were 11A, flight missile number 6, and 2A, the static test missile recently removed from Edwards Rocket Base. 2A will be used as a training and facility checkout missile. These are 2 of the 6 missiles which left the plant during the quarter. The future capabilities of a missile are best indicated by progress in laboratory testing. Here at Point Loma, engineers test the larger missile components and systems and perform those functions which require greater than normal safety precautions. The fourth quarter was highlighted by tests of B-series components. Here you see one of a series of tests which simulated a launching of the B-series full-thrust missile. Hydraulic rams provide the simulated thrust. The task involves qualification and design evaluation of the more complex launcher equipment. This vertical arm supports lines which connect to the missile nose cone. The receptacle simulates the nose cone. In these tests, engineers checked out the tower and umbilical disconnect lines prior to shipment of the tower to Cape Canaveral. In operation, the nose cone lines will be disconnected just prior to launch. The support arm will pull the lines clear of the missile before it is committed to flight. An additional test stand was constructed during the quarter for proving out nose cone separation. In flight, the warhead will separate from the airframe prior to re-entry into the atmosphere. In this test, engineers were checking out fittings and clearances. In December, first full-length drops were conducted. This was a shakedown of operating equipment, instruments, and control circuits. In flight, B missiles will jettison booster engines and components in this manner. The Point Loma site is also used as an outdoor laboratory for hazardous testing of smaller components. This apparatus was set up to determine the maximum structural strength of a missile component. Each test, large or small, is completely instrumented, providing a record of all test parameters. The elbow joint carries liquid oxygen from tank to engines. In this test, it was pressurized with liquid nitrogen to bursting point. This component proved to be more than twice as strong as specified by operational requirements. These tests are only representative of the type of activity performed in the laboratory program. Testing is paced by long-range needs of the Atlas program. Construction of the new astronautics plant is nearing completion. By the end of 1957, building exteriors had reached their ultimate sizes and shapes. First unit to be activated at the new site was the centrifuge. The 10-ton boom and test chamber will subject ICBM components to extremes of stress, vibration, and temperature. Objects weighing up to 2,000 pounds can be accelerated to 170 miles per hour or 121 revolutions per minute. Maximum force generated is 100 Gs. In gravity tests, engineers may vary temperatures from 100 degrees below zero to 350 degrees above. Provision has been made to include vibration equipment at a later date. At the end of the year, workmen were near completion of the walls and roofing for the 500,000 square foot factory building. Were pouring concrete footing for heavy machinery, installing glass in the 6-story engineering building, had completed steel work for the cafeteria, and were enclosing a space for the electronic computer in the largest of the engineering laboratory buildings. The 252-acre site will centralize Atlas research and development and provide facilities for future astronautics projects. This is Sycamore Canyon Stand 2, to be the first site for Series B Atlas simulated flight tests. The facility is complete except for miscellaneous items of ground support equipment. Missile 1B will be the first bird to be static fired here. Stand 2 is located about 1/2 mile over the hill from Stand 1, where testing continues on A-series missiles. Later testing included 3 hot runs, in which a preliminary progressive shakedown was made of the accessory power supply, vernier engines, and booster engine. A will be the first to be static fired with a 300,000-pound thrust booster engine. Delivery was to the Convair assembly building, where field checkout was accomplished during November. This structure is to be used by Atlas associate contractor teams. These groups are assisting in the integration of prime contractor systems into the Atlas weapon system. In the fourth quarter of 1957, activity at all three Atlas test stands was marked by changeover to a more advanced phase of the test program. This is stand 1-1 on November 20th. On this date, Missile 5A was removed from the test stand after having completed a total run time of 620 seconds, 550 of which were accomplished during the fourth quarter. Removal of this test missile was premature due to a ruptured bulkhead sustained during run 113. Since primary objectives of the test series had been accomplished, the decision was to proceed with conversion of the test stand to accommodate B missiles. Progress at the 1-4 battleship stand was highlighted by the changeover to B-series engines and associated systems. Mating of the B thrust section to the battleship tank brought the three power units and missile systems together for the first time. The first sequence of runs was planned as a progressive shakedown of engines, systems, ground support equipment, and operating procedures. The third run was the first in which maximum thrust was attempted. Scheduled test duration, 3 seconds of main stage operation. The boosters, sustainer engine, verniers, and APS unit performed satisfactorily. At stand 1A, missile 14A was raised into firing position on December 13th. Tests with this bird will complete the static test program for the Series A missiles. 14A differs from previous static test missiles in that it will be the first fired with the 300,000-pound thrust booster engine. In this engine, the two thrust chambers are bell-shaped, permitting greater thrust buildup within a shorter chamber. The 270,000-pound thrust chambers were conical in shape. Static tests here will aid in establishing reliability of flight components. In addition to this, Missile 14A will remain in standby condition as a backup missile for resolution of flight problems. On November 1st, Flight Missile 12A arrived at Cape Canaveral after an 8.5-day trip across the continent. This missile had been modified in part at the factory. These field modifications followed the design changes made at San Diego and backed up by tests at Sycamore Canyon and Edwards Rocket Base. Preparation for flight began at Hangar J. Major design changes involved the thrust section. Here, craftsmen have cut back the fairing around the engine compartment. Width of cut, 31 inches. The engine nacelles were shortened by 16 inches. The redesigned heat shield is 3/8-inch fiberglass bonded to stainless steel. It has been moved forward 31 inches. Within the engine compartment, Rocketdyne technicians replaced critical aluminum plumbing with stainless steel and existing wiring with high-temperature wire. Forward pod sections were reinforced. The task was completed with the installation of the redesigned turbine exhaust duct. Fuel-rich turbine exhaust gases will be directed into the missile airstream. On November 21st, Missile 12A was transported from Hangar J to Launch Complex 14. With the erection of 12A, there were two missiles in flight position. This one, Missile 12A, at Pad 14, and at Pad 12, Missile 10A. On November 27th, Missile 10A was static fired. The test was scrubbed after 8.5 seconds of main stage operation due to a malfunction in the fuel supply system. This incident delayed the scheduled flight of 10A, reversing the flight order of the two missiles. On December 10th, Missile 12A appeared ready for flight and was scheduled for a 35-second captive firing to check all systems except release. Records taken during this run were analyzed to determine the proper functioning of missile systems, ground support equipment, instrumentation, and operating personnel. Satisfactory performance was attained, and Missile 12A was committed to the flight countdown. The countdown began during the early morning hours, December 17th, 1957. It proceeded with only a few minor holds. This was the missile at T-minus 41 minutes. All preparations had been completed, and technicians began pumping the 13,000 gallons of liquid oxygen to the upper tank. A quick check was made of all systems. Instruments indicated a go condition on each. Missile 12A was launched at 12:39 p.m. Eastern Standard Time, December 17, 1957, on the 54th anniversary of the Wright brothers' flight at Kitty Hawk. The third Atlas flight was completely successful. From instrumentation, engineers determined the time of engine shutdown as 127 seconds after launch. At this time, the missile had attained a velocity of 5,220 nautical miles per hour, 3 times as fast as a rifle bullet. From this point, trajectory rise carried 12A to a height slightly over 100 nautical miles. Point of impact was 490 miles downrange from the launch site. Total time of flight, 8 minutes and 38 seconds. Restoration of the launcher was begun immediately. Next missile to be launched from this complex will be 13A. At Pad 12, Missile 10A was scheduled for launch as the 4th flight missile. Vernier operation represents the next added step in flight evaluation. This advance was made possible because of the excellent results obtained with Missile 12A. The 4th flight of Atlas is scheduled for January 1958. The objective? To carry the program one step further in the progressive development of the total weapon system.